Yes. So hello everyone, welcome. So for the past 7 to 8 videos, we are seeing previous year solutions of linear algebra, UPSC Mathematics Optional Paper 1, right? So already we completed 2018 to 2024. So in this video, we will solve 2017 paper, right? So it has 5 questions for 70 marks. Sorry, 6 questions for 70 marks, right? Okay. So if you haven't watched all the previous videos of 18 to 2024 solutions, I strongly recommend you to watch all the previous videos before watching this year solution, right? Yes, so we'll start our first problem. So all are very simple and easy problems. So we'll do this quickly. So I'll try to finish this within 1 hour, right? Okay. Let A is equal to let A is equal to let A is equal to 2, 2, 1, 3. Find a non-singular matrix P such that P inverse AP is a diagonal matrix, right? So we need to find a non-singular matrix P such that when you multiply P inverse AP, that matrix has to be a diagonal matrix. So how to find that matrix P? That matrix P is nothing but the eigenvector matrix. That's it. We can find this matrix provided if this matrix is diagonalizable. But that and all we don't need to prove this. This is a 10 mark question only, right? Okay. So first what we'll do is we will find the eigenvector matrix that will be the required matrix P. So first we will find eigenvalues for this matrix and then we will find eigenvector corresponding to each eigenvalue and then we'll put it in a matrix form that eigenvector, then that matrix will be P matrix. I'll tell you how, right? Okay. Now first we have A is equal to 2, 2, 1, 3, right? Now we will find the eigenvalues. So we will find the characteristic equation. For characteristic equation, you can find determinant of A minus lambda I. If equal to 0, we will find eigenvalues, right? You can use that, or we know the characteristic equation for a 2 by 2 matrix, right? The characteristic polynomial is given by lambda square minus S1 lambda plus S2. If I equate to 0, the roots are the eigenvalues, right? Roots are the eigenvalues. So we will have lambda square minus what is S1? S1 is traces. So 2 plus 3 is 5 plus what is determinant is 6 minus 2. So which is 4. If I equate to 0, I will have the eigenvalues. So sum is minus 5, product is 4. So sum is minus 5, product is 4, right? So we will have what? Sum is minus 5, product is 4. So we will have minus 4 minus 1. So lambda square minus 4 lambda minus lambda plus 4 is equal to 0. So if I take lambda outside, lambda minus 4, minus 1 outside, lambda minus 4 equal to 0. So that means lambda minus 1, lambda minus 4 is equal to 0. So lambda is equal to 1 and 4 are the eigenvalues, right? 1 and 4 are the eigenvalues for this 2 by 2 matrix. Now we will find eigenvector corresponding to each eigenvalue. We will find eigenvector corresponding to each eigenvalue. These are very simple, right? Okay. So eigenvector corresponding to lambda is equal to 1. So we will find eigenvector corresponding to lambda is equal to 1, right? So we will find eigenvector corresponding to lambda is equal to 1. A non-zero vector x is called eigenvector corresponding to lambda if ax equal to lambda x. That is a minus lambda I of x is equal to 0. This x is called eigenvector corresponding to the eigenvalue lambda, right? Corresponding to the eigenvalue lambda. So you know how to find that all, right? So very simple. So we'll directly we'll do this fast. So a minus lambda I. So a is 2, 2, 1, 3 minus lambda is 1 first. So 1, 0, 0, 1 times x is equal to 0. So this will be 2 minus 1 is 1, 2, 1, 3 minus 1 is 2. Let us call x to be x1, x2 and this is a 0 vector, right? So we have x1. So this is nothing but we have to find x1, x2. This x1, x2 is nothing but what? Solution of homogeneous system, right? Solution of homogeneous system. So we'll solve this homogeneous system directly. So we will write the augmented matrix A comma O directly. So we have 1 2 0 1 2 0. So if I reduce this, rank of A is 1, right? So rank of A is 1. So 1, 2, 0, 0, 0, right? So that means one free variable, we have an equation x1 plus 2x2 is equal to 0. That means x1 is equal to minus 2 times x2. So let us put x2 to be equal to k. Then x1 will be minus 2k. Therefore, the eigenvector corresponding to this set is given by an infinite set. That set is given by minus 2k comma k, or k times minus 2 comma 1. Right? This is the one of the eigenvector is minus 2 comma 1. If I multiply any scalar with this, we will have infinitely many eigenvectors, right? So one of the eigenvector corresponding to lambda is equal to 1 is minus 2 comma 1. Now similarly, we will find eigenvector corresponding we will find eigenvector corresponding to lambda is equal to 4, right? We will find eigenvector corresponding to lambda is equal to 4. So a minus lambda I x is equal to 0. This is called eigenvector. So we have to find a minus 4i of x is equal to 0. So a is 2213 minus 4 times I of x is equal to 0. So we will have minus 2, 2, 1, 3 minus 4 is minus 1, right? Of x1, x2 is equal to 0, 0. So again, we have to find x1, x2, which it turns out to be the solution of turns out to be the solution of this homogeneous system of linear equations. So you reduce to echelon form. So minus 2, 2, 0, 1 minus 1, 0, right? So this is equivalent to what? You just shift the rows and then you multiply 2 and then add. So just shift the rows and then you multiply 2 and then add. So you will have this system of equations. So we have x1 minus x2 is equal to 0. So that means x1 is equal to x2. So we have one free variable. Let us take x1 to be equal to k. This implies x2 is also equal to k, right? So we have number of free variables n minus rank of a. So n is 2 here because x1, x2 two variable, rank is 1. So one free variable. You assume x1 to be k. This implies x2 is equal to k, right? Because one free variable. Since one free variable. Okay, so therefore the eigenvector corresponding to this eigenvalue is given by k comma k. So k times 1 comma 1 and this k belongs to real number. So one of the eigenvector is 1 comma 1 for eigenvalue that is one of the eigenvector is 1 comma 1 for lambda is equal to 4 eigenvalue, right? So you just form a matrix P to be, right? I'll write here conclusion, write it here. The matrix P, right? Find a non-singular. That means there can be many. One of the non-singular matrix P is given by, so you just form the eigenvector matrix. So minus 2 comma 1 in first row and then 1 comma 1 matrix in second row. If you find P inverse AP, that P inverse AP will be a diagonal matrix, right? That P inverse AP will be a diagonal matrix. Okay, you can verify that this is the non-singular matrix P is given by this. If you want, you can also verify. You just find the value of P inverse AP. You know how to find inverse for this matrix, and then you multiply A, you multiply P, you will be getting a diagonal matrix. And diagonal elements will be the eigenvalues. Check it out and comment. Repeat. This P inverse AP you have no. You just find the P inverse AP, right? You just find P inverse AP, just find determinant for this 1 by determinant. You just find inverse for this matrix P, which is 1 by determinant into adjoint. You know how to find adjoint for 2 by 2 matrix, right? You shift these two elements, you multiply minus minus with these elements. You can find inverse for this matrix. With the inverse matrix, you multiply A and then you multiply P, you'll be getting a diagonal matrix. Diagonal entries will be the eigenvalues, right? You will always get eigenvalues as diagonal entries. That is, you will get the diagonal entries as 1 and 4. Okay, so we'll move on to the next problem. So 10 mark question. So if you want to find a non-singular matrix P such that P inverse AP is a diagonal matrix, that P is nothing but your eigenvector matrix, right? See, you cannot always find a non-singular matrix P such that P inverse AP is diagonal matrix for all matrix. If this matrix is diagonalizable means you can find a non-singular matrix P. If this matrix is not diagonalizable means you cannot find a non-singular matrix P, right? That are all theory. Here this matrix is diagonalizable. You will be having, yeah, you can see distinct eigenvalues. If this matrix, if you have distinct eigenvalues, that matrix is always diagonalizable. Okay. So we move on to next problem. This problem I'm not going to do because in 2018 paper itself we have solved the same one. Prove that the similar matrices have same characteristic polynomial, same repeated question. I'm not going to do this. So if you want to have a solution, refer 2018 PYQ. So refer 2018 PYQ, right? So you refer 2018 PYQ for solution for this, right? We already solved this. So we know that two matrices are similar. A is similar to B if there exists an invariant matrix P that such that P is equal to P inverse AP. Just refer that video, right? Okay. So we'll move on to the third problem. Um, Consider a mapping A from R4 to R3 where A is a matrix given by 1, 2, 3, 1, 1, 3, 5, minus 2, 3, 8, 13, and minus 3. Find a basis of the image of A and the basis for kernel of A, right? So again, very simple problem, right? Every time they will be asking the same similar kind of problem. So we'll do this now. Okay. So first what we'll do is we will find the basis for image of A. That is, we need to find the basis for range space. Um, so you just find the rank for this, right? You just find the rank for that matrix. From that you can find the basis for image of A. The matrix of A is given by 1, 2, 1, 2, 3, 1, 1, 3, 5, minus 2, 1, 3, 5, minus 2, 3, 8, 3, 8, 13, and minus 3, right? Okay, so we'll reduce this to row echelon form. So we have R2 is transformed to R2 minus R1, R3 is transformed to R3 minus 3 times R1. So this is equivalent to 1, 2, 3, 1. 1 minus 1 is 0, 3 minus 2 is 1, 5 minus 3 is 2, minus 2 minus 1 is minus 3. R3 minus 3 times R1. You multiply 3 here, it will be 6. So 8 minus 6 is 2. You multiply 3 here, it will be 9. 3 minus 9 is 4. You multiply 3 here, you multiply 3 here. So minus 3 minus 3 will be minus 6. Now we have to make this element as 0. So R3 is transformed to R3 minus 2 times R2. So this is equivalent to 1, 2, 3, 1, 0, 1, 2, minus 3. You multiply 2 and then you subtract. You will getting this entire row to be equal to 0. This is in row echelon form, right? This is in row echelon form. And you can see rank of A is equal to what? It is equal to 2, right? So what is the basis? See, it need not be a unique set. It need not be a unique set. So one of the basis is given by one of the basis, one of the basis of image of A is given by 1, 2, 3, 1, comma 1, 2, 3, 1, comma, and then 0, 1, 2, 1, minus 3. It is one of the basis, right? So these two are linearly independent and these two vector will span your image space, right? Will span your image space. Now we need to find the basis for kernel. See, here you can see the rank is 2 and we know rank plus nullity is equal to 4, right? That means your nullity will be equal to what? Nullity will be equal to 2, right? Nullity will be equal to 2 because by Sylvester's theorem, rank plus nullity is always equal to dimension of domain space. Dimension of domain space is 4. So rank is 2, nullity will be 2. That means your null space will have two linearly independent elements in your basis, in the basis, right? Uh, we will find that. Now first we will find null. Now we will find null space of T. So what is null space of T? Null space of T consists of all those vectors, in R4 such that that is mapping to 0. That map is given by A such that Ax equal to 0, right? So we need to find all those vectors in R4 that maps to 0 vector of R3. So let us say that x is given by x1, x2, x3, x4, right? Let us say that x is x1, x2, x3, x4. So we need to find x1, x2, x3, x4. A is 1, 2, 3, 1, 1, 3, 5 minus 2, 3, 8, 13, and minus 3. Let us say that x is x1, x2, x3, x4 is equal to 0 vector of R3, 0, 0, 0. So this reduces to an homogeneous of linear equations, right? X1 plus 2x2 plus 3x3 plus x4 is equal to 0, right? Just a minute. Okay. And then we have x1 plus 3x2 plus 5x3 minus 2x4 is equal to 0. And then we have 3x1 plus 8x2 plus 13x3 minus 3x4 is equal to 0. So we will solve this homogeneous system of linear equations. So we will find the augmented matrix, right? We will find the augmented matrix 1, 2, 3, 1, 0. And then we have 1, 3, 5, minus 2, 0, 3, 8, 13, minus 3, and 0. So if I reduce this to row echelon form, I'm going to write the same matrix here, which is 1, 2, 3, 1, 0, 1, 2, 3, 1, 0, 0, 1, 2, 0, 1, 2, minus 3, 0. Then we have 0, 0, 0, 0, 0. Right? So here you can see how number of free variables is what? Number of free variable is, so number of free variable is n minus rank of A. So n is total number of variables, right? So total variable minus rank of A. So we have four variables x1, x2, x3, x4, and a rank of A is equal to 2. So that means we have two free variables, right? And what is the equations we have? X1 plus 2x2 plus 3x3, x1 plus 2x2 plus 3x3 plus x4 equal to 0. And then x2 plus 2x3, x2 plus 2x3 minus 3x4 equal to 0. So we have two free variables. Let us assume x3 to be equal to k1, x4 to be equal to k2. Right? Call this as 1, call this as 2. So from 2, what is x2? x2 is 3 times x4 minus 2 times x3. That means 3 times k2 minus 2 times k1 is the value of x2. From 1, what is x1? x1 is minus 2x2 minus 3x3 minus x4 minus 2 times x2 is 3k2 minus 2k1, 3 times k1 minus k2. So this will be minus 6k2 plus 4k1 minus 3k1 minus k2. So if I collect a1, k1, 4k1 minus 3k1 is k1, minus 6 is minus 7k2. So therefore, our solution space x1, x2, x3, x4 is given by the set x1 is k1 minus 7k2 and then 3k2 minus 2k1, or I'll write it in a k1 k2 format. So this is minus 2k1 plus 3k2 minus 2k1 plus 3k2 comma k1 comma k2. That means this is spanned by k1 times 1 comma minus 2 comma 1 comma 0 plus k2 times minus 7 comma 3 comma 0 comma 1. This k1 k2 belongs to real number. Right? Now we can see the solution space. The solution space is spanned by the vector 1 minus 2 1 0 and minus 7 3 0 1, right? So the basis for null space of T is given by 1 comma minus 2 comma 1 comma 0, one of the bases minus 7 comma 3 comma 0 comma 1, and what is nullity of 2? Dimension is 2, that we already know, right? Because rank is 2, obviously nullity has to be equal to 2, because rank plus nullity is equal to 4. So that's it. So when we are done with the third problem, so it carries 15 marks. See how simple it is, right? So here instead of reducing the matrix, we can use the matrix directly here for finding the solution of this homogeneous system of linear equations, right? Okay, so first problem is based on finding a non-singular matrix P such that P inverse AP is a diagonal matrix. How to find the matrix P? The matrix P is nothing but your eigenvector matrix. And second one is a repeated question from 2018. So I left this question. Third one is we need to find the basis for image of A and kernel of A. Okay, can you move on to the next one? So fourth one, again a very simple proof based on dimension theorem. So I hope everyone aware of the dimension theorem, right? Okay, so we'll do this question now. Is it clear up to now? Okay. Okay, so here U and W are distinct four-dimensional subspace of V. So we have a vector space V, and U and W are distinct four-dimensional subspace of a vector space V. It can also intersect also, right? It can be like this, or it can intersect also. U and W can intersect also. Just for some understanding, I've drawn the diagram. U and W can also intersect also at some points, at some vectors. Can have non-order intersection also. Let's suppose U and W are distinct four-dimensional subspace of a vector space V, where dimension of V is 6. Find the possible dimension of the subspace U intersection W. So U intersection W, what are the possible dimensions it can have, right? This is W. What are the possible dimension this U intersection W can have? Okay. Uh, so what is dimension of U? Dimension of U is 4. And what is dimension of W? Dimension of W is 4 again. And what is dimension of V? Dimension of V is 6, right? Okay. Now we need to find possible dimensions of U intersection W. Okay. So we know that dimension of U plus W, dimension theorem, right? This proof is already available in linear algebra content section in a playlist. If you want, you can go through that. For 10 mark, I don't think we don't need write proof. So dimension of U plus W is equal to dimension of U plus dimension of W minus dimension of U intersection W, right? Now, dimension of U plus W, dimension of U is 4, dimension W is also 4, minus dimension of U intersection W. So that means dimension of u intersection w is equal to 8 minus dimension of u plus w, right? Call this as star. So we have got dimension of u intersection w in left hand side. Now we need to analyze about the dimension of u plus w, right? We need to understand about the dimension of u and w, right? Okay. Now can I say uh, we see that, can I say that u and w will be a proper subset, will be contained in u plus w, and this u plus w is contained in v? Yes or no? Obviously, right? This u will be contained in direct sum u plus w, and then u plus w will be contained in v. All are subspace only. Okay. Now we have u is contained in u plus w, and u plus w is contained in v. That means dimension of u is less than dimension of u plus w is less than dimension of v. What is dimension of u? 4 is less than dimension of u plus w is less than dimension of v is 6. Yes or no? Is this step is clear? It need not be strictly contained in. It can also be proper or improper also. Let us put some inequality here. Right? So dimension of u plus w is always, so dimension of u plus w can be 4, or dimension of u plus w, dimension of u plus w can be, dimension of u plus w can be 4, or it can be 5, or it can be 6, right? Dimension of u plus w can be 4, 5 or 6. So from star, dimension of u intersection w can be equal to what? If dimension of u plus w is 4, this u, this u, right? Okay. If dimension of u plus w is 4, then dimension of u intersection from star, dimension of u intersection, this can be equal, if this is 4, this will be 4, right? Or dimension of u intersection w equal to, if this is 5, this will be 3, right? Or dimension of u intersection w is, if this is 6, it will be equal to 2, right? So from star from star let us call this as double star. So from star and double star, right? From star and double star, dimension of u intersection w can be 4, or it can be 3, or it can be 2. Now whether it can be 4, that's the next question, right? Whether it can be 4. Now you can see that u and w are distinct subspace, right? Since u and w are distinct, right? Since u and w are distinct, u intersection w is not equal to u as well as not equal to w. Yes or no? Because they are distinct. That means dimension of u intersection w cannot be equal to 4. Cannot be equal to dimension of u, and also cannot be equal to dimension of w. Both are 4 here. That means this is not possible. Not possible since that explanation. So therefore, dimension of u intersection w is equal to 2 or is equal to 3. That is the conclusion. Okay, dimension of U intersection W is either 2 or it is 3. Is it clear? Very simple, right? See, I'm just using dimension theorem. This U plus W lies between 4 and 6. That means U and W can be 4, 3 or 2. Since U and W are distinct, that means intersection cannot be equal to U or W. That means dimension of U intersection W cannot be equal to dimension of U and cannot be equal to dimension of W. Both are equal to 4 here. So that means dimension of U intersection W cannot be equal to 4. This is not possible. This is not possible. Right? This is not possible. So 3 and 2 are possible dimension of U intersection W. Right? So we'll move on to the next one. So last two problems. Time is 10:06. Okay. So I'll try to complete within 2025. Consider the following system of equations in x comma y comma z. For what value of a does the system has a unique solution, and for what value of a and b it have more than one solution. So more than one means automatically it will be infinitely many solution. So first what we'll do is we'll reduce this to, we'll write this in echelon form, sorry, augmented form. So a comma b. So what is a comma b? 1 2 2 1 1 a 3 3 1 11 a and b, right? Okay, so we will reduce this to row echelon form. So we have R2 is transformed to R2 minus R1. R3 is transformed to R3 minus R1. So this is equivalent to 1, 2, 2, 1. So 1 minus 1 is 0. Here we have a minus 2. 3 minus 2 is 1. 3 minus 1 is 2. 1 minus 1 is 0. 11 minus 2 is 9. Here we have a minus 2. Right? Here we have a minus 2. Here we have b minus 1. Right? Now what we'll do is we'll make this element as 0. So what we'll do for that? What we'll do for that is, so we have R2 is transformed to, so we'll multiply a minus 2 with the R3 is transformed to, we will multiply a minus 2 with R3, we will multiply 9 with the R2, and then we will subtract, right? So this is equivalent to, so we have 1 2 2 1 0 a minus 2 1 2 0. We are multiplying a minus 2 here, 9 here, and then we are subtracting. Here we are multiplying a minus 2 and then we are subtracting 9 here. So this will be what? A minus 2 whole square minus 9, right? Here we are multiplying a minus 2. So a minus 2 into b minus 1 minus 18, right? So this will be my a minus 2 b minus 1 minus 18. So this will be my third row, third element, right? Okay. Okay. So we'll simplify this. We'll simplify this. For what value of a and b does the system has a unique solution? Okay. Can we simplify this to some more extent, or else we'll directly move on to the problem? Okay, we'll directly move on. So the first thing is, for unique solution, right? For unique solution, this alone not equal to 0 is enough, right? If this number is not equal to 0 means rank of A and rank of A comma B both will be equal to 3. Very simple ideas, right? If this number is not equal to 0 alone, will guarantee my the system has unique solution. So that means for unique solution, what is the condition? Rank of A and the rank of A comma B both are equal to 3. So A minus 2 whole square minus 9 should not be equal to 0, right? So that means A minus 2 whole square should not be equal to 9. So you search all this. So A minus 2 whole square should not, A minus 2 should not be equal to, A minus 2 should not be equal to plus or minus 3. A minus 2 should not be equal to plus or minus 3. So that means A minus 2 should not be equal to 3 and A minus 2 should not be equal to minus 3. That means A should not be equal to 5. Here A should not be equal to minus 1, right? So that means A can take any real number except except uh, except 5 or minus 1. That means for unique solution, A can take any real number except minus 1 and plus 5. And I don't care about the value of B, right? B can take any real number. B can take any real number. I don't care about the value of B. Because if this number is non-zero, right? If this number is non-zero, is alone enough for a unique solution, right? I don't care about the value of B, right? So this number will not be equal to 0 if A is A, this number will not, this number, that means A can take any real number, but it should not take minus 1 and 5. If it takes minus 1 and 5, then this will be equal to 0. It should not be equal to 0. If this is not equal to 0 means A should not be equal to 5 and minus 1. That means A can take any real number except 5 and minus 1. Now for infinitely many solution, second subdivision, for infinitely many solution, right? For infinitely many solution, this should also be 0. This should also be 0. Yes or no? Then only you will have rank of A and rank of A comma B both are equal to 2. So rank of A comma B both to be equal to 2. So that means we have A minus 2 whole square, A minus 2 whole square minus 9 should be equal to 0, and I'm putting and this should also be 0. A minus 2 B minus 1, A minus 2 B minus 1, A minus 2 B minus 1 minus 18 should also be 0. Both should simultaneously should be 0, right? Okay. If this is equal to 0 means we already solved, right? A minus 2 whole square is 9. That means A minus 2 is plus or minus 3. It means A minus 2 is equal to 3 or A minus 2 is equal to minus 3. That means A is equal to minus 1 or 5. So A has to be minus 1 comma 5 and we have to find B, right? A can be minus 1. If A is minus 1, what is B? If A is minus 1, what is B? This will be minus 1 minus 2 minus 3. 3 minus 1 is equal to 18. So 3 ones are 3 6 are. So B minus 1 is minus 6. So B is equal to minus 6 plus 1. So B is equal to minus 5. Right? So one pair is minus 1 comma minus 5 is one pair. If A is equal to plus 5, what about the value of B? So 5 minus 2 is 3. 3 into B minus 1 is plus 18. 3 ones are 3 6 are. So B minus 1 is 6. So B is 7. So 5 comma 7 is another pair. So there are only two pairs, right? There are only two pairs for AB such that this has infinitely many solution, right? So the what they are asking, for which pair of values? Uh, the pair of values, the pair of values for which it has infinitely many solution. More than one means infinitely many solution. It has infinitely any solutions are given by -1 comma -5, and there are two pairs 5 comma plus 7, right? First corresponds to A, second element corresponds to B. Is it clear? See, they haven't asked about no solution. Suppose if they ask you for what value of A and B, it has no solution, means for no solution, this number should be 0, this number should not be 0. Yes or no? For no solution. If this is 0 means rank will be 2. If this is non-zero means rank will be 3. So you just make it of the same thing. If this is 0 means A can be -1 or +5. If A is equal to -1, right, you find the value of B, but this should not be equal to 0. You find B, right, by putting this number is not equal to 0, you find B is not equal to. That means for A is equal to -1, you will have B to be infinitely many values except some. Can you just visualize? If A is equal to -1, here if A is -1, okay, I'll put it down. I'll load for no solution. Um, these are this additional, right? These are this additional information, additional info. For no solution, uh, this should be 0, right? This should be 0. A minus 2 whole square minus 9 should be 0. This will be 0 when A is -1 comma 5, and is it visible, this color? Okay, and this should not be 0, that is A minus 2 and A minus 2 B minus 1 minus 18 should not be 0. So if A is equal to -1, what is B? If A is -1, you'll be getting B is not equal to -5, right? That means you will have an infinite set for this. So -1 comma B, such that B belongs to any real number except -5. This is one set of pair, infinite set of pair. Again, if A is equal to +5, if A is equal to +5, you'll be getting B is not equal to 7. You will be having another set of infinite pairs 5 comma B, and this B belongs to all real number except 7. Is it clear? So -1 comma B belongs to all real number except -5. If this happens, you will get this term to be 0, this term to be non-zero. That means you will be getting no solution. Right, you will be getting an infinite number of possible values for A comma B. The A comma B are given by A is -1, B can take any real number except -5. This is one infinite set. And again, if A is 5, B can take any real number except 7. This is also an infinite set. So for infinite set of pair A comma B, you will have no solution. Is it clear? Okay, this is an additional info only. Okay, so for this problem, uh, the answer will be -1, -5, 5 comma 7 for this one, and for this one, A belongs to all real number except -1 and 5, B belongs to real number. Okay, but they haven't asked B. For what value of A only they are asked. Okay, so we'll move on to the final problem. See, very simple problem. It carries 15 marks. So we'll move on to the last problem. Again, basic theorem, very conceptual, basic conceptual theorem that prove that the eigenvectors corresponding to distinct eigenvalues are linearly independent, right? Okay. So already we have proved like eigenvectors of similar matrices are orthogonal, right? Already that we have proved. So here is a very standard theorem that the eigenvectors corresponding to distinct eigenvalues are orthogonal, right? Okay. So we'll prove that. See, there are many proofs. I'll prove differently, right? I'll prove by mathematical induction. I always like to prove by mathematical induction. So we'll prove by mathematical induction. To prove that the eigenvectors corresponding to distinct eigenvalues are linearly independent. So let lambda 1, lambda 2, lambda 3, and so on up to lambda n be n distinct eigenvalues, and let x1, x2, x3, and so on up to xn be the corresponding eigenvectors. Eigenvectors always non-zero, right? A non-zero vector x for an eigenvalue lambda is called an eigenvector if ax is equal to lambda x. This x is called eigenvector for for eigenvalue lambda if ax is equal to lambda x. So for lambda 1, x1 is the eigenvector. This implies ax is equal to lambda x, right? And for lambda 2, x2 is the eigenvector. That means ax2 is equal to lambda 2 x2. Just apply the definition. A non-zero vector x is called an eigenvector for an eigenvalue lambda if ax equal to lambda x. Here x is the eigenvector for lambda. For lambda 1, x1 is the eigenvector we have assumed. For lambda 2, x2 is the eigenvector, and so on up to for xn is the eigenvector for lambda n eigenvalue, right? Okay, this is by definition. Okay, now what we need to prove, this set x1, x2, x3, and so on up to xn is linearly independent. We need to prove, right? To prove, let us call the set as to be B. We need to prove that the eigenvectors eigenvector set x1, x2, x3, and so on up to xn is linearly independent. So we need to prove this set is linearly independent, right? I'll finish in 8 minutes. Let x1, x2, x3, and so on up to xn. We need to prove the set is linearly independent. So we'll prove the set is linearly independent by we will prove by mathematical induction. We will prove by mathematical induction on n. Right? I'm going to prove this by on. This on is very important. On which you are going to be mathematical induction. So you know what is mathematical induction, right? I've already explained in PYQs of some other year. So you need to prove it is true for n is equal to 1. You assume it is true for n is equal to k. You prove it is true for n is equal to k plus 1, right? Okay. So we'll prove this. First, for n is equal to 1. If n is equal to 1, our set V consists of only one vector. Yes or no? A set consists of single vector is always linearly independent, which is here linearly independent set because we have only one non-zero vector. See this, all these x are non-zero vectors, right? All these be corresponding eigenvector, all non-zero. That is the definition only, right? So a single set consisting of non-zero vector is linearly independent. So which is linearly independent as your x1 is not equal to 0 because eigenvector are non-zero vectors. This is linearly independent set. Hence it is true for n is equal to 1. So if n is equal to 1, the set is linearly independent. Now we will assume it is true for n is equal to k. This is step 2, right? Step 2. We will assume it is true for some n is equal to k, right? So we'll assume for n is equal to k, it is linearly independent. That is, let us assume it is true for n is equal to k. So let us assume x1. Let us assume x1, x2, x3, and so on up to xk is linearly independent, right? We'll assume it is true for n is equal to k. That is, this set is linearly independent for n is equal to k. So by assumption, there exist some scalars, there exists some or else we'll just apply the definition of this set is linearly independent. Suppose if this can be done as a linear combination, let us say some c1 x1 plus c2 x2 and so on up to ck xk. If this linear combination is 0, this means what? All your c1, c2, c3 and so on up to ck's are 0 because this set is linearly independent. If you are writing as a linear combination, then all the scalars are equal to 0 because the set is linearly independent set. Right? I'm assuming everyone knows the basic idea, right? If not, you just go to the playlist linear algebra. You will have conceptual videos there. Okay. This is our assumption. Now, what is step 3? To prove it is true for n is equal to k plus 1. That is to prove that is to prove the set x1, x2, x3 and so on up to xk, comma xk plus 1 is linearly independent. If I show this, then our problem is over. So we'll prove that it is true for n is equal to k plus 1. Is it clear up to now? Okay. So that is to prove, that is we need to prove c1 x1, c2 x2 and so on up to ck xk plus ck plus 1 xk plus 1. If this linear combination is 0, I need to prove all the scalars c1, c2, c3, ck and so on up to ck plus 1. All are 0. I need to prove, right? Okay, so we'll prove this. So let us call this as some star, right? Let us call this as some star. I'm going to do two things on star. Is it clear up to now? I was seeing only two comments. Okay, no problem. I'm going to do two things on star. From star, I'm going to do two things. From star, I'm going to take a on both sides, right? I'm going to take a on both sides. So a of c1 x1, c2 x2, and so on and so on. ck xk, ck plus 1, ck plus 1, ck plus 1, xk plus 1 is equal to 0. So if I take a inside, c1 ax1, c2 ax2 and so on, ck axk and so on up to ck plus 1 a of xk plus 1 equal to 0, right? Okay. Now what is a times x1? It is nothing but lambda x1. By definition, ax equal to lambda x1. Now what is a times x2? See, these are standard theorems only, right? Don't think that these are all they are asking. Very simple, standard. Every time when you study linear algebra, it is just a very what I can say, elementary theorem that everyone should know, right? If you are studying linear algebra, the eigenvectors are linearly independent for distinct eigenvalues. So lambda on x1, lambda x2, and so on. Ck, this is lambda k xk, ck plus 1. This lambda k plus 1 xk plus 1 is equal to 0. This is by definition of this, right? Because ax1 is lambda 1 x1. Okay. Call this as double star, right? Call this as double star. Now, what I'm going to do is I'm just going to multiply. I'm just going to multiply lambda k plus 1 in star, right? I'm just going to multiply lambda k plus 1 throughout in star. What do you will have? C1 lambda k plus 1 x1 plus C2, just multiplying lambda k plus 1 x2, and then we have what is star here? Ck xk, ck lambda k plus 1 xk, and multiplying ck plus 1 what I'm doing. So from star I'm multiplying lambda k plus 1 throughout. So C1 lambda k plus 1 x1, C2 lambda k plus 1 x2, and then ck plus 1 lambda k plus 1 xk plus 1 equal to 0. Call this as triple star, right? Now what you do is you just subtract these two, right? You just subtract these two. That is, you subtract double star minus triple star, right? You just subtract these two. If I subtract these two, what you will have? These two terms will get cancelled, right? Same terms. Here, if I subtract, if I take C1 outside, you will have lambda minus lambda k plus 1 x1. If I subtract these two, C2 lambda minus lambda k plus 1 x2, and so on up to ck lambda k minus lambda k plus 1 xk is equal to 0. We are getting this linear combination to be 0. This is non-zero. Why? This is not, all these are non-zero. Why? Because all eigenvalues are distinct. All eigenvalues are distinct. This is also not equal to 0 because eigenvectors are non-zero vectors. But this linear combination is 0. That means what? All these C1, C2, C3 and so on up to CK, we can do like, or else we can do like, this is not equal to 0. Okay, we don't care about that x1, x2, x3, right? Okay, I'll tell by some other thing. I'll tell by some other thing. So we have C1, we can do like, how can I say, so we'll prove like we are proving this term is equal to 0. Yes, we have proved. Yes, we have proved. Is there any visualization from this? Actually, I tried out some new thing, but we come to the proof. We are having this linear combination to be equal to 0. Yes. From the assumption, we already assumed that it is. We already assumed that. Okay. From this, can we conclude? Can we conclude? Can we conclude the set x1, x2, and so on up to xk is linearly independent? Can I conclude the set is linearly independent? Because we already know all C1, C2, Ck are zeros. So this is 0. All these coefficients are 0. That means our x1, x2, x3 and so on to xk are linearly independent set, right? Uh, if the set is linearly independent, then star becomes what is star? See, we need to prove this only. We need to prove this is 0. We need to prove this is equal to 0, right? So we'll take the LHS part. C1 x1, C2 x2 and so on up to Cn xn plus Ck plus 1 xk plus 1. So we'll start with this. So we have 0 plus Ck plus 1 xk plus 1. Yes or no? So is equal to 0. This means what? Our Ck plus 1 is also equal to 0. So already our C1, C2 and so on Ck are 0. Now we have put Ck plus 1 is also 0. So this implies our set x1, x2 and so on up to xk, xk plus 1 is linearly independent, right? So hence the proof. Very simple proof. So actually I tried a new thing, but it works. What we did is we are proved by mathematical induction on n. So for n is equal to 1, it is true. For n is equal to k, I'm assuming it is true. That is, this set is linearly independent set. With this assumption, I'm trying to prove it is true for n is equal to k plus 1. So that is, I need to prove that if this Ck plus 1 is 0, then I can prove the set is linearly independent because I already know that this C1, C2, all these Ck's are 0. So my aim is to prove that this Ck plus 1 is 0. So for the Ck plus 1 to be 0, first I am showing that all these are equal to 0. And then if this is equal to 0, this is non-zero, right? Because this is a non-zero vector, eigenvector. That means Ck plus 1 has to be 0. So that means all these here are 0. Therefore, the set is linearly independent, right? So that's it. So this paper has 6 questions. So all these 6 questions are some very good paper. Actually, this is. So in the next video, we will solve 2016 paper, right? So thank you. All the best. See, I think this is clear, right? Just a minute, I'll explain this part alone. This part, right? How I am proving this to be 0 because um, we conclude that by assumption we see that this is a linearly independent set, right? So I can write like since x1, x2 and so on up to xk is linearly independent. So therefore these C1, C2 and so on up to Ck's are 0. Right, that is what I'm concluding here. We can conclude this x1 linear independent, and this is by assumption. That means our C1, C2 and so on up to Ck's all are 0. And I'm substituting all these here. This is Ck, Xk, all these are 0. See from this Since this is linearly independent, because we know this set is linearly independent, right? That means all these C1, C2, C3 up to and so on up to Ck all has to be 0. So I'm just substituting here. So this will be 0. So Ck plus 1 also 0. So already C1 to Ck 0 and then Ck plus 1 0. So from that we say that this is a linearly independent set. That is the idea, right? Okay. Okay. So we'll see you next class. Thank you. All the best.